All right. So welcome everyone, and thanks for joining this SZ4D virtual workshop. My name is Shoshu Han. I'm a marine seismologist at University of Texas Institute for Geophysics. And my co-organizers of this workshop are Donna Shillington, Nathan Benz, and Eduardo Contreras-Frias. So together, we welcome you to this workshop, and we look forward to discussing with you the planning of this new seismic imaging experiment offshore central Chile. So we would like to thank SZ4D for the support, and especially many thanks go to Anais for her help to make this happen. Thank you so much, Anais. Oops. Ooh. Go back. So I would like to start with a very brief introduction of SZ4D. So SZ4D, or subduction zone in 4 dimension, is a community-driven initiative for a long-term interdisciplinary research program to understand the limits and possibilities of predicting geohazards. To study geohazards, we choose subduction zones because subduction zones are natural laboratories for geohazards, including earthquakes, tsunamis, volcanic eruptions, and landslides. And 3 subduction zones are chosen to be the primary sites for SZ4D efforts. So Chile, and Cascadia, and Alaska. And the SZ4D efforts include both instrumentation and scientific activities. The working group recommends 70% of instrumentation efforts and 50% of scientific activities in Chile. So Chile is really the main study site for SZ4D. As you can see from this figure, I don't know if you can see my cursor or yes? Okay. So one core component of SZ4D experiment is the instrumentation, like the onshore, offshore instrumentation. The number 1 is mega array, and number 3 is surface array. So Donna will talk more about these in her talk next. The mega array is a seismic and geodetic array with instruments on both the offshore part and the onshore part to monitor subduction fault behavior. And in order to know, to put the observations in context, and also in the first place to design and implement the array, we need to understand the subsurface structure and velocity. So let's take a step back. Like we all know that Chile is very long margin. It's from 18 degrees south to about 46 degrees south. So over the past summer, the US SZ4D community and Chilean AndesNet have discussed where to put this mega array and Volca array and surface array, mainly the targets for instrumentation. And here is the results from the April SZ4D all hands meeting, and we chose Central Chile for instrumentation. And then in June, AndesNet hold a meeting and voted to set this orange S-shaped region as a primary region for instrumentation. So as you see that the offshore portion of this lightning bolt is between 28 degree and 34 degree. And when we review, because as I mentioned, we really need to understand the subsurface structure and velocity in order to design and implement the array, and also to put all the observations from the array into context. When we reviewed the existing active source seismic data, we found that the Chilean margin is unevenly covered by active source seismic data. So these lines are existing lines, and you can see that the southern part is well covered. However, the central part, central Chile part, only has sparse data coverage. And most of the data were acquired by shorter streamers, like 3 kilometers or less, that significantly limited its imaging capability for deep structure. So that is the motivation to collect modern seismic imaging data in order to better understand the subsurface structure and properties of this part of the margin. So we will propose to conduct a community experiment with RV lenses, take advantage of its advanced imaging capability to acquire long offset multi-channel seismic reflection data and wide-angle reflection and refraction data recorded by OBSs and onshore seismometers. We plan to do that along a number of 2D lines covering the region between 28 degrees South and 34 degrees South. And our expected data products include high-resolution seismic reflection images that will give us a lot of information about the structure, and also high-resolution velocity models, which can be used to infer subsurface physical properties. And because this will be a community experiment, we aim to make the data and data products accessible to the community as soon as they are available. So the objectives for this workshop is we hope to seek input from the community about how to best design and plan this project, so it will maximize opportunities for scientific investigations and also collaborations within the SZ4D program. The schedule for the workshop is here, and we have part 1 to give the background and motivations. We will hear from Donna about SZ4D scientific questions, and then Sergio will review the earthquake history of Chile, and then Eduardo will give us an overview of existing active source seismic data in offshore central Chile. And then we will have 5 minutes break, and then part 2 of the workshop. This was the original schedule, but because quite a few of our speakers got COVID from the SZ4D leadership meeting last week. And so one speaker has to cancel the talk, and the landscape and seascape talk will be given by Donna on behalf of Christine Morel. And then, so this is our updated schedule for part 2, but we will hear from Elise, Laura, and Donna and Damien about perspectives from different disciplines. And then the third part will be a discussion session. So we will have different breakout groups. We have 4 themes here for subduction input, megathrust, upper plate faults, and sediment transportation. But we originally we wanted to have the breakout groups according to themes, but then we later think maybe a better way to do it is to randomly assign people to different groups, and each group can discuss all 4 themes. And after the breakout discussion, we will have a synthesis session and all hands discussion to report back the results from breakout group. And so this is my last slide. I would like to introduce the SZ4D Code of Conduct. Because SZ4D, we aim to build a diverse and vibrant science science communities, and we hope that we will treat one another with respect and value diversity of views and opinions. So here are the expected behavior and unacceptable behavior, and I will just leave the slides here. And one last thing I want to mention is we have some international participants. If you click the CC at the bottom of your Zoom window, you can enable the closed caption, and you can choose the language you prefer. It has English and Spanish, so you can choose whichever language you prefer. So I will stop here, and I thank everyone again for joining this workshop, and I look forward to the discussion. All right, so stop. So I guess next, Donna will give the talk.
Can you see my screen okay?
Yes.
Excellent. Hi, good morning, everyone. Thank you so much for joining today. just to provide a little bit of a context for the discussion we're going to have, I'm going to do a very brief introduction to SZ4D. I think many people on this call have already heard a similar introduction many times, but it's important we're all on the same page. All right, so as Shosho said, the SZ4D is a community initiative to try and develop a ambitious new effort to study the science behind subduction zone hazards, and in particular to understand the limits and possibilities, underline, of predicting geohazards. And if you want to know more about this effort, there was a implementation report that was released almost a year ago. It's beautiful and it's full 176 pages, but there is an 8-page executive summary, and this will describe a lot of the things that I'm going to try and review in my my brief remarks here. All right, so the kind of science behind the SZ4D has been really defined by three different working groups, kind of framed around different components of the subduction system. So we have the faulting and earthquake cycles working group, magmatic drivers of eruption working group, and landscapes and seascapes. And in addition to these working groups, two integrative groups, the building equity and capacity in geoscience, and the modeling collaboratory for subduction. So, these kind of combined groups and the people that have been a part of them defined the science drivers of SZ4D, which are outlined in the implementation report. And so kind of the overarching science questions, which we want to have in our minds as we think about, a new project focused for SZ4D are here. So the first one is when and where do large damaging earthquakes happen? Which is, of course, the faulting and earthquake cycles question. How do transcrustal processes initiate eruptions at arc volcanoes? How do events within Earth's atmosphere, hydrosphere, and solid Earth generate and transport sediment across the subduction zone landscapes and seascapes? What fraction of the subduction zone's energy budget goes into building and shaping subduction zone land and seascapes? So you can see that those three questions kind of track to the three main disciplinary working groups focused on earthquake, volcanic, and surface processes. And then the final question comes from the building equity and capacity in geoscience. How can we transform the mindset of our geoscience community to embrace education, outreach, accessibility, capacity building, diversity, equity, inclusion, and social justice as critical components for the success of SZ4D and future scientific endeavors by the geosciences community? So those are the overarching questions of SZ4D, but I just wanted to drill in a little bit to, in particular, the when and where do large earthquakes happen, and to the which is the FEC question, and to the landscapes and seascapes question here. So for kind of under that large umbrella question for faulting and earthquakes, we have these 4 sub-questions. I won't read them all, but the first question focuses on kind of faults across the subduction zone system and how they interact at different temporal and spatial scales. The second one really is about what controls the slip behavior on the megathrust itself. The third question concerns precursory behavior and its existence or not, and what causes it. And the fourth question is about shallow slip and processes that would promote tsunamigenesis. So the faulting and earthquake side of things, and then for landscapes and seascapes, we already saw these 2 questions, but the first one is really about, how do phenomena within the atmosphere, hydrosphere, and solid Earth kind of conspire to control the transport of sediment across the subduction zone landscape. And the second question is about, the fraction of the energy budget that's going into building and shaping the subduction zone land and seascapes. So I've run through those very quickly because I believe that many of you have heard these before. But the purpose to review them is that, of course, we want any new program that's trying to tackle, that's focused within the SZ4D community to help have a chance to tackle some of these questions. So the overall strategy that kind of emerged from a lot of discussions in these SZ4D committees to tackle those questions has, multi-prongs. So one component are really ambitious observational arrays, which Shosho already has mentioned. So a mega array, a primarily seismic and geodetic amphibious network to monitor subduction zone slip behavior, Volc array, multi-sensor arrays on volcanoes to monitor their behavior, and surf array, which is sort of an array to monitor active surface processes across the system. But to kind of contextualize these arrays, which are intended to be deployed for, longer period of time to see behavior, we need other things. And so to understand what those observational arrays are telling us. So, field geology to give us a longer time perspective of subduction zone behavior and deformation. Geophysical imaging to show us, what is the configuration of the subduction zone that's making the behavior observed by these arrays. And so, of course, what we are discussing here kind of falls under that category. And then also experimental and numerical modeling studies to kind of synthesize and bring together these observational components, and training and outreach to kind of engage a larger community in this work and empower them to work on all these data. So that's kind of the strategy that's described in the implementation plan. And as Shosho said, after a very careful evaluation of basically every subduction zone segment in the world, the SZ4D committees recommended kind of pairing a focused study of the Chilean subduction zone, which has ideal attributes for all of the different scientific components of SZ4D, with comparisons with the Cascadia and Alaska subduction zones. Once the Chilean subduction zone was identified as of special interest to SZ4D, we've now, over the last years, been having a really deep and conversations with Chilean and Argentinian scientists about what are the opportunities in this subduction zone. And as Shosho described, the Chilean Argentinian community through AndesNet had a meeting last June to kind of discuss and then ultimately vote on regions of the margin to focus on, and the kind of area that emerged as ideal and with overlapping opportunities for all these different array components was here within the central Chilean subduction zone. All right, so that's kind of where we are. And I just wanted to say a little, this is my last slide, about where SZ4D is headed from here. So over a long effort, there's been a definition of these science questions, a selection of these particular regions to focus on for the observational component. And kind of the road forward is that SZ4D as an organization is trying to map out a way towards proposals for infrastructure to fund the design and implementation of those ambitious arrays, and also targeting proposals to seek funding that would help us to continue to have mechanisms to bring the community together and to do science together. And so those are listed here. But after the implementation report is released, there's now the opportunity for anyone to start to tackle SZ4D science questions now by writing proposals to other available programs. And so the effort that Shosho is leading here kind of falls in that category to identifying an opportunity and a need to tackle SZ4D science questions in the nearer term by putting in a proposal, and also to collect a data set that would be really valuable for informing some of these other efforts. So I think that is what I had.
Thank you very much, Donna. Do we have any questions from the audience? Okay. If not, let's move on to Sergio's talk on earthquake history of the Chilean margin.
Well, so
we saw that you have started screen sharing, but I haven't seen your screen yet.
Do you hear me well?
Yes, now it's good.
Okay. Okay. Well, obviously we'll speak about solution in search. Introductions, there is different kind of networks. In this case, some pure in the traplet in the scapular, so in the American cruise level, they had in very the cruise
Excuse me, Sergio, like you're cutting
Yes.
in and out. Like your voice is like it's not continuous. Like I don't know like if it would help if you turn off your video, like maybe that could help. Hello?
Yes. Oh, sorry. Now hear me.
Yeah, we can hear you.
Perfect. Well, I then the focus searching and quick typing and when we can hear
Sergio, se te escucha cortado.
There was a suggestion that maybe someone else can share Sergio's slides, so maybe then it helps.
it's okay too. No, apparently the problem is the one.
Shall we move to the next speaker and Sergio reconnect? Maybe.
Or like Anais, could you?
Yeah.
We can
Yeah.
we can hear Sergio, so there's still the.
Yeah, we can. Can you hear me, Eduardo?
We can hear you, Eduardo.
Maybe I can give my presentation first, and Sergio can get an assistant for his connection.
Yes.
Yeah. Okay. Eduardo will be giving us an overview of existing active source seismic data.
Okay. Can you see my screen?
Yes.
Yes. Okay. Okay. So my presentation is something like a review of historic and existing data offshore central Chile. But first, I would like to say something about the very global regional tectonic setting. So actually, Chile have like two main subduction zones where the Nazca plate subduct beneath South America, but also the Antarctic plate south of the Chile rise, or Nazca Antarctic Spreading Center. And there are many oceanic features of or high relief, like the Juan Fernandez, which is colliding with central Chile, offshore Valparaiso, just is central Chile and the study proposed area of the subduction 4D. Another main oceanic feature is the Chile rise, an active spreading center, which is colliding here in northern Patagonia and separates the subduction on the Nazca and Antarctic plate. And there are at least 6 hotspot tracks on the oceanic plate formed by mantle plumes like the Nazca Ridge, which is subducting here offshore Peru, the Juan Fernandez Ridge itself, the Copiapó Ridge and Taltal Ridges and the Iquique Ridge. There are minor hotspot ridges, but still they are very prominent features of the oceanic plate. The plate age of the Chilean margin is, of course, 0 here of the Chile true projection, where the Nazca Antarctic Spring Center is colliding here, the collision, and becomes older to the north and to the south. And for example, in central Chile, the age is between 45 to 35 million years old. And there are several also fracture zones, many fracture zones, which produce abrupt changes in the thermal age, so thermal age contrast, and different thermal state, let's say. And concerning our study proposed area subduction 4D, the plate age is between 36 and 47 million years old at the trench axis. And in this area, it's very interesting because we have a dramatic or prominent change in the sediment thickness at the trench axis. This plot shows the the sediment thickness at the trench axis and the age of the oceanic plate at the trench axis. And here is this is the Juan Fernandez Ridge, offshore Valparaiso. Within the study area of the subduction 4D, and we have this dramatic change from sediments less than 300 meters, 400 meters, up to 2 kilometers or more in south central Chile, between the Juan Fernandez Ridge and the spreading center in the Chile true projection. And then farther south, the sediment thickness increased again in the glacier area of southern Patagonia. So the Juan Fernandez Ridge behaves somehow like a barrier for sediment transport to the north. And the North Chile desertic arid area, and there is no mass sediment at the trench. So this is the study subduction, sorry, the proposed study area for this project, for this proposal, and we can see here a dramatic change on the sediment thickness. So also take into consideration that the sediment thickness, according to some author, is no, so the thick sediment thickness south of the Juan Fernandez Ridge is not something really very old, or not something like in geological time very large, but is instead something like more recent, just during the last 5 million years, during the Pliocene interglaciation, or after the post-glaciation period, it was an increase of the sediment thickness about 5 million years ago. And also in this sediment thickness increase is coincident with a decrease in the plate convergence rate from, let's say, from the Miocene to the present. So just during the last 5 million years, we have the condition of a very thick sediment thickness at the trench and low or relative low, well, it's not low compared to Cascadia to Antarctica, let's say 6 centimeters per year, 7 centimeters per year, which is the current rate or convergence rate today. And we have these conditions which in principle favors sediment accretion and formation of accretionary prism. And as a first order, some people, some authors can say that the collision of the Juan Fernandez Ridge with the central Chile is produce a transition from sediment or subduction erosion in the north with little sediment in the north to the possible formation of sediment accretion or basalt accretion, underplating, and subduction, sediment subduction. Depends on many other factors. But at least the sediment thickness is there and has potential effects on the accretion mode. Okay, let me now show you, or go to the data, well, the Chilean margin has been studied by several research cruises, many projects from mainly from Geomar, from Germany. They have acquired more than 20 2D lines using OBS, so wide angle seismic data, more than 20 since 1995 to the present. The last cruise was this year, in February to April, and here in north central Chile. And I found three, okay, there are like 3D seismic experiment, so 3D seismic geometry for seismic refraction. And the last one was this year in north central Chile. There's a very old one but also by Germans here in Valparaiso, by the way, the study area of the study of this proposal. And there is another 3D seismic experiment offshore Iquique, here in the area of the 2014 earthquake, by the way, by the Marcus Lancet with American, granted by Ann Trejo from Oregon State University. Regarding multi-channel seismic reflection profiles, there are plenty of data that you can see all this line here and the specification here and the leyenda, and acquired by BGR, the German Geological Survey, also the Chilean oil company, Lamont, in the 90s by Conrad, Texas, and Oregon State by Marcus Lancet, mainly in 2016 and 2017, and some short streamer lines acquired by Geomar. Yeah. I will show some examples of wide angle seismic profile, yeah, within our or proposed study area. Valparaiso, yeah, this is a 3D seismic experiment. This is the geometry. And these are the result of Colin Selt, 1999, 2003. Okay, so here we have the oceanic plate, the oceanic crust subducting the Valparaiso for our basin here in the accretionary prism. Yeah, this is the inverting 3D tomography and some slide, you can different depth. Yeah, this is one example. I'll show you one more. This is a wide angle profile acquired by Geomar in 2001, 2002, on board the research vessel Sone at 31 degrees south, also within the proposed study area of the subduction 4D. And here we have the oceanic crust subducting low velocities in the mantle here, and a very small, here's the snore of the Juan Fernandez. This is the O'Higgins-Simons collision zone. And we are not here north, the sediments at the trench are very little. And we have a very small frontal prism, and also a very interesting abrupt change in the velocities from the middle wedge to the inner wedge here, further landward. Yeah, about here is the coast. This is the area, by the way, of the Ijapel 2015 8.1, 8.2 megathrust earthquakes. Yeah, this is the same line. And also there's another one at 32 degrees, just 100 kilometers to the south, just north of the Valparaiso Basin. This is the 4R Basin. And the model shows frontal prism, the mojo, the oceanic crust. Also, these abrupt change in velocities landwards. And well, here is a relative uplifted feature. And also, well, this area is very active seismically, and there's the area of the collision of the Juan Fernandez Strait. We have an earthquake of 7.8 in 1985, and sometimes we have a seismicity, a crustal seismicity, I will say a shallow crustal seismicity in the area. These events are from 2008 and 2009, recorded by the Chilean Seismological Network. A little bit further south of the Juan Fernandez Strait, we have a very thick, relatively thick sediment thickness of about 2 kilometers. And here is the Maule area of the Raptor area of the 2010 earthquakes in magnitude 8.8. And these are the models for Maule, which shows a very large accretionary prism, about 40 to 50 kilometers wide. Okay. Also, that will be very interesting for the landscapes group. A little bit south of the Maule Raptor area, there is a single, very short line, profile night, acquired by Geomar in 2008. And in that area, we have a very massive mass wasting event with a volume of 24 cubic kilometers. Yeah, we call it the Riloca slide, and just offshore the town Riloca. And we have observed this very spectacular mass wasting event. Very, very steep walls. And here the sedimentary material observed by the velocity model. Yeah. So Maule area, I think there are plenty of these events. Please also have a look of the paper of Jacob Gersen of mass wasting event in South Central Chile. One of the very spectacular features in Central Chile is, as I say several times already, is the Juan Fernandez Strait. This is the velocity model by Hadrian Cobb from Geomar. Offshore, this is the trench, so seaward of the trench. And I think, well, we have learned many things about the volcanic edifice of the sea mounts, of the Higgins sea mounts. And maybe we should do an effort to map these sea mounts here in the collision under subduction, which is the San Antonio and Papudo sea mounts already under subduction. Yeah, maybe that will be one point to discuss later. Also, I would like to show some example of multi-channel seismic profile recorded by the Marcus Lancet. Yeah, just to show you how is now the quality compared to the past data. This is acquired by Oregon State, University of Chile in 2016 in the Raptor area of the Iquique earthquake. They have a 3D geometry and many multi-channel seismic reflection data using a streamer of 8 kilometers, sometimes 12 kilometers. And there's nice results showing the complex faulting system and I would call it paleo 4R basin. Yeah, this is a erosive margin at present, but they have a very complex 4R basin and or maybe two prominent reflectors and complex faulting system in the 4R basin. I mean, this super reflector in another one. Yeah. So here With the Lancet, you also, so you have, of course, the chance to map very with high quality the seismic reflection image, but since the streamer is so long, 8 kilometers, 12 kilometers, sometimes 15 kilometers, you can also use the shot to obtain the velocity models for shallow depth, like in this example. So you can do like, let's say, full wave inversion, so obtaining the image and the velocities, yeah, with the Lancet. Also, Boma from Guiomar, a ex-PhD student, worked with the deep reflectors and from the Marcus Lancet, and they obtained the subduction interface, which is a very interesting and important constraint for our target. They map the subduction interface in the area of the Iquique earthquakes. Yeah, this is also our Lancet data. In 2017, Nathan Banks and co-authors from Texas and from Santiago, Universidad de Chile, they map 3 raptor areas, the Maule, the Illapel, and the Valdivia. And this is an example of Valdivia. Valdivia is the northern part of the raptor area of the 1960 megathrust earthquakes, the largest earthquake ever recorded. And this is the northern asperity. And these, you can see the quality of the data of the image. And this is in depth, time, sorry, this is in time. You can see the detail of the sediment thickness, the top of the oceanic crust, and underplating or underthrusting sediments, yeah, beneath the shelf. For comparison, I will show you some data from SONE by the German Geological Service, BGR, before 2003, so 20 years ago already. And they, this is a streamer of 3 kilometers long, but still, they are very high quality to map this is the four basin of Arauco. Arauco is Concepcion at 38 degrees. We have the Mocha Island, and still the data are very good, but I'm not sure. Yeah, maybe we can do also some BP modeling. Another example is Central Chile at 32 degrees, the same study area of now of the subduction 4D. And here we can see the subsidence of the 4R basin near the trench, mainly because of subduction erosion. Another example, well, there are many examples we can see later in the breakout. But one of the points that we discussed with the organizer of this meeting is that subsurface imaging with active seismic source data in this region is relatively sparse and was acquired with much less capable equipment than modern standards. Yeah, so the streamer is short, 3 kilometers. The former streamer is relatively short than state-of-the-art current techniques. So which limits the image quality and velocity models of the deep structure. This is a technical point. And also, there are some seismic gaps that I would like to point out. For example, in the seismic refraction and reflection, we have some gap here in the area of La Serena, or here. Yeah. And this area is also important because, well, this is the offshore seismic gap. Yeah, we have some seismic refraction data in the north. Valparaiso has been studied, but please take into account that this seismic refraction data offshore Valparaiso, which is the most populated part of Chile, were acquired in 1995 and 2001. Yeah, so our relative old seismic refraction data, the density of the station, the spacing is very large. So it's something that we can consider for mapping or revisit some lines. And here there's absolutely nothing seismic gap in farther north and La Serena region, Coquimbo, and for example, as the 2015 earthquakes, this is the Raptor area approximately, and just we covered with pre-existing data, just the half of the Raptor area. So we have still this gap. It was an historic earthquake in 1922, magnitude 8.5 to 8.7 moment, seismic moment probably. And still we don't know much about this Raptor area. And well, in 2010, we have these many lines acquired by Lancet and by the Chilean oil company in this area already. The Juan Fernandez Ridge, which is here, the collision, well, we have to discuss if we should revisit again. Yeah, I think this is my overview talk, and that this is the main institution that took part of all this acquisition. Nevertheless, there are many data. I think some people consider Chile one of the most studied margin, despite his length so long. This is the global. Let me show you this one, the very old global seismic data. But okay, this is a matter of discussion. So I will stop here. Thanks.
Thank you so much, Eduardo, for this excellent overview of the existing data. Yeah, I think this map is very illustrating of the lack of the data for our proposed study region, and also like thanks for showing the examples from both north and south with modern seismic imaging, and in comparison with some old data in our study region to show the potential that that with the new data we can significantly improve the imaging of the subsurface. So do we have any questions from the audience for Eduardo?
Donna.
Yeah, thank you so much for that overview. I was wondering if the data that were collected by the Chilean oil company are generally available, or if those require special permission to access, or how's the access to those data?
This data has been working by Juan Diaz, and I think Juan Diaz is around. Maybe he can answer, no?
Hello. Good afternoon or good morning. It depends on where you are. Yes, during my PhD, I processed the 4 seismic lines of the 6 that were acquired by research vessel Conrad for the National Oil Company of Chile. Yeah. So this is a well-known system that was used by Conrad in 1988, was that. And it is interesting that my main, well, maybe not the only one, but one of the main conclusions I came out with during my PhD is that north of Mocha Island, the behavior of the subduction process is this accretion through, I forgot the word, when you get imbricate sheet layers, whereas to to the south of Mocha Island or Araucan Peninsula, you get more a subducting channel of sediments, and then underplating through this stacking from below. And I got the data just for free, but we have to take into account that this data was acquired before GPS was developed. So for some purposes, the quality of the data is not that good, not because of the seismic system, but because of the positioning. Yeah. So I think and this data was already, so it's available through Lamont Doherty. So you can get from one side or the other side. Yeah. So it was when the Conrad was going to map the and to image the triple junction, because it had to be imaged before the ODP went there in 1991 or so. I don't recall exactly. So during the same cruise, previously, the Conrad acquired those seismic lines. That is the story.
Okay, I hadn't put it together with the Conrad data. Thank you so much.
Jacob?
Yeah, thanks, Eduardo, for the great overview. Maybe not a question, but just a comment to add that what's usually forgotten is that there are also hundreds of sediment echo sounder lines available. They do not resolve the plate boundary at depths. They are also not very helpful when it's too steep, but if you're interested in sediments, upper slope sediments, these data often resolve at least the upper meters to tens of meters of the slope sediments. And that's also like the power sound data from the German ships and other sediment echo sounder data. That's also available, but often forgotten. Yeah, thanks, Eduardo, for the great talk.
Thanks. Ignacio?
Hi, Eduardo. Thank you
Hi.
for the great presentation, super clear. So I have a question, and actually, I believe with Nathan, we were talking about this a couple of months ago. What happened with the sediment? How dramatic is the change when you are, for example, in front of Rio Valdivia, Rio Biobío, Chacao Channel, or Guafo? Do you think it's a very interesting, it's an interesting place, that area in front of the rivers, or where you can have a very high load of sediments, which can change properties?
We know that when we have the rivers, we have the big canyons. So the canyons, the offshore canyons are the continuation of the rivers. And then we have a fans formation at the trench. We have a higher sediment input for sure. But regarding the properties of the sediments, well, we have to obtain some samples to answer that question.
Very nice. Thank you, Eduardo.
Welcome.
I can add something on that. There is a paper, actually 3 papers, but by Todd Thornburg, who made his PhD at Oregon State University. And the last one, the paper in 1990 by Todd Thornburg, precisely answers your question, Ignacio, because he imaged that using CMark II side scan sonar, and he took also samples from the fans from not only but mainly from the Biobío Canyon and from the Calle Calle Canyon. So
Thank
there
you.
are that paper is very valuable, I would say. Those 3 papers by Todd Thornburg.
Wow, thank you, Juan. Can you share that link maybe in the chat? That would be nice to have it if you have it on hand. Thank you.
Hey, thank you all for the questions and comments. I think we need to move on to Sergio's talk. We're running a little over time for this session. So Sergio, are you ready to?
Yes, I think so. I think that now I'm in the good internet connection.
Great.
Do you hear me well?
Yes. We're hearing
Much
fine.
better.
Yes, and now I need that Eduardo screen off, please.
Eduardo, if you can stop sharing, then Sergio can share his screen.
Now you see my screen?
We're still seeing Eduardo's screen.
Oh.
Okay, great. Thank you.
It's ready for me. Do you see my screen? Do you hear me well?
Yes.
Both.
Okay, I will try to do a shorter presentation to don't extend too much. Then I will focus in this presentation in earthquake, historical earthquake that occur in central Chile, and only in the event that occur in the megatrust in the plate interface. Then I will don't speak about other interesting and destructive earthquake like the intraplate intermediate depth earthquake, and also the crustal event that in Chile also we have some active faults close to the seas. But we focus in the megatrust, and in this event for central Chile, that this part that explained Eduardo is mainly controlled by a huge event that occurred almost 300 years ago in 1730. This is this extension that I tried to show you with these purple lines. Then this has an extension the almost 800 kilometers. In all these places, we have chronics of the destruction in the towns of this period, also the tsunamis. This event was studied recently by different groups. They proposed that this huge event, maybe with a magnitude around 9. It's a big, large earthquake. Now also in the coast of Chile, we have some paleoseismic studies. In this, for example, in this picture of the work of Pinadura, we can see a trench in the Chilean coast, in the Quinteros Bay, and we can see the different evidence of the tsunamis. Then they can form the tsunami associated to this big earthquake, the 750, but also with the other big tsunamis, big tsunamis that affected the central Chile zone. And this, in the datation, they found that this occurred with a period of time of some centuries, 2 centuries, 5 centuries. Then if we can, maybe we can do an average for this big earthquake in central Chile of one of each 3 centuries. Then with this very roughly average, this event occurring 1730 is very important for the central Chile, because in this almost 300 years, we don't have a big earthquake like this. In the north part, yes, we have other big earthquakes. It's Atacama, 1920, and magnitude around 8.6. And also in the central south part, we have the recently event is a Maule earthquake, but also it's a big earthquake. But in all this part, we have the 1730 big megatrust earthquake. And if we move now to the events magnitude around 8 that occur in this part of Chile, we can divide this in this event that I grouped here with these more yellow lines that describe this rupture that around 200 kilometers length. And in the north part, we have the events that occur in the same, almost in the same place where occurred the recently Illapel earthquake in 2015. Then other earthquake a little smaller occur in this zone in 1943, previously in 1980. If we move to the south, we have La Ligua earthquake in 1971 and earthquake magnitude 7.9. And also the sequence of the event in Valparaíso that are very important, because Valparaíso is an important port in Chile, and also is in front of Santiago, that is the capital and the main city. And 1985 and 1906 are very important and destructive earthquakes for the Chilean population. And also these events are well recorded. And here, if you you see are important earthquakes, are magnitude 8, and here the recurrence time we speak is not centuries like this bigger one, if not a few decades. Then we take a few decades. In central Chile, we have an event magnitude 8. One thing that I think is important to highlight is all these events are mostly occur in the deeper part of the plate interface, maybe in this classification proposed by Torley, Yukanamori, and the group of today. These all events occur in the zone C and zone D, the middle of the plate interface, or in the deepest part of the plate interface. The only exception is the Yapel earthquake that is maybe a little larger in magnitude than the others one. Yapel has a very irregular shape, but in some part he's very close to the trench. The other ones, all these events magnitude 8 has no tsunami or very few tsunami and instrumental tsunami if you want. Then we propose that all these one, the older ones, magnitude 8, that occur not close to the trench. And this is a picture of the Juan Carlos Baez, only to see the difference between a big earthquake like Maule. This is our vector, the GNSS vector displacement. Here is the scale of the vector, 2 meters. Then Maule move around 5 meters, 6 meters on part of the coast. Eyapel around 2 meters. But in central Chile, we have other earthquakes that occur not in each few decades, each few years are the magnitude 7, for example. If we have a good instrumentation, we can well recorded, for example, with this that occurred in Valparaiso in 2017, a magnitude 6.9, where we have some GPS deployed just in front of this event that occurred here. And we can see very interesting things. For example, that this event magnitude 6.9 was preceded by a slope slip event. This 7 also occurred in the middle of the plate interface. But it's only a context figure. Here is the Juan Fernandez Ruiz that explained very well as well. Then if we did a short summary about which earthquake, historical earthquake in the last centuries have occurred with a rupture that broke close to the trench, we have, of course, the largest one, that almost 9 maybe magnitude, the 70-30, big tsunami. And also the Yapel earthquake, that this is a slip distribution. There is many models. Here I put one of the Emil Klein, but almost, I don't know. Mostly of the slip model are very similar. The rupture of the earthquake, the Yapel moved especially to the north with a part in the deepest part of the contact, and also a slip very clear, very close to the trench. This is the Yapel that trigger an important tsunami in this zone. Then it's only these 2 events we know well that are close to the trench. What's happened with the others? And if we look more smaller events, here I put for the time only the aftershock of the Yapel. And this is a picture. Here in this white space is the slip rupture of the main shock, and the aftershock are in the boundaries of this slip distribution. Also, there is some outer rise, but apparently there is not many aftershock close to the trench. This dark blue zone is the trench, but for this event, it's very difficult to us know exactly where it occurred because we don't have good velocity models, and then we don't have good localization. But 3 months after of the Yapel main shock, we have this interesting sequence that has several earthquakes and are very close to the trench. And in particularly occurred 2 events, 619 separated, but around 2 hours. And with the 619, we can study well and we can localize with different techniques and to know exactly where they happen. And then if we look his focal mechanisms, we can observe here a schematic profile of this zone where they occur. They are inverse events during the plate interface and very, very close to the trends, similar that all the events of this sequence. And also, if we do the more continuous working in this, and this was the work of the Javier Ruiz and his group, he modeled this event, that this is the slip distribution of these two 619. And he also found that these events are very, very close to the trend, are two events 6.9. Interesting, they have here a schematic picture, and the epicenter of these two 6.9 events are just after of the frontal freeze in a zone that is fracturated rock here, but here is more igneous and more competent rock. And then in this part, that is close to the trench, because like so Eduardo, we are at the north of the Juan Fernandez Ridge. It's very small, the frontal freeze. We have these two events are a 619. Then for this reason, we don't have you want an instrumental tsunami, but if this event for some reason could be an 6.3, 6.4, maybe we can be speaking about a tsunami earthquake, but it's not the case because it was in the limit, I think so. But the message is these are very, very close to the trend, and in central Chile, it's possible to have this kind of events. One thing interesting, at least for the seismologists thinking, is this event that I put here are very close of the post-seismic distribution. This is the cumulative post-seismic distribution of the Yapel. The blue lines is the co-seismic. The post-seismic has this irregular also shape. This is the work of Roxanne Pisander, Gianmartino Chiet, et al. And the events that occur 3 months after the main shock are very close to the post-seismic, and good hypothesis maybe is the post-seismic of the Yapel earthquake trigger these two very close to trench events. But this is an observation. Also in central Chile, we have many swarms of clusters. They are, unfortunately, I don't have a good picture, but all the time we have swarms in magnitude 4, magnitude 3 in some case. And the truth is we don't study regularly. Then for this is an information that is not clear that to put on picture. I'm sorry for this one, but it's very interesting because in the same part we have cluster, many of them swarms, that occur persistent in the time. And for example, we looking for the swarms that occur in the boundaries of the Yapel earthquake, and we have this heat map that with the number of the events in different period of time from the 2003 to when occurred the Yapel earthquake. If, for example, here that is in front of the Los Vilos, I named Los Vilos swarm, but I don't know if other person named this word similar, but are events very small, occur, very recurrent, very persistent. Also, Roxanne Pisander, in the same part, when he studied the slip rate, the post-seismic, found that it's increasing in some period, and she proposed that slow slip event occur during the post-seismic of Yapel. Occur a movement apparently all the time in this part. Then other hypothesis that maybe we can discuss and try to prove is true is these persistent swarms could be associated with more hydrated zones in the plate interface, and maybe are more hydrated because are some some fractures in the Nazca plate that are more have hydrated sediments, maybe because this is are very regular. Maybe we can associate it with the slow slip. At the moment, we don't have to do the well associations, with the exception of this proposition of the rocks and there, because the magnitude are very small and we don't have the good instrumentation to test this hypothesis. Then I try to do very fast, but the summary is this one, and this is, I think, the main topics. One is these are the events. We have huge event in central Chile, magnitude 9, 70-30 is in the main zone of the central Chile, and the boundaries for the north is the Atacama, 19-20-20. For the big earthquake in the southern part, we have Maule. We have each few decades magnitude around 8. We can see that these 8 mostly, I don't know why, they occur in the deeper part of the plate interface, in the deepest, in the middle of the plate interface. Only Yapel earthquake, that is maybe the bigger of this magnitude 8 earthquake, because Yapel is an 8.3, maybe an 8.4. Its rupture is close to the trench, but all these Valparaíso, La Ligua is in the deeper part. We don't know if the smaller one events occur close to the trench. Maybe yes, but with the localization that we did at this moment, we don't have a good constraint because we have problem of velocity models and others, the distribution of the stations, of course, but all these are online. But these two aftershocks of the Yapel are very interesting because for me it's very clear, close to the trench, just after of the accretionary freeze. Then I think that this is the fast summary I could do of the Central Chile earthquake. I'm sorry for the previous problem.
Thank you very much, Sergio. This is very informative. So I think considering the time, and we are 20 minutes behind schedule, I think we can save time for the discussion session. So how about we take a 2 minutes break? Sorry about cutting your break short. And then we're back to the room at 9:15 Pacific time, like 11:15 my local time. And then we continue with part 2 of this workshop. Okay. All right. Thank you very much, all the speakers, for section 1. We will hear from scientists of different disciplines and about how active source seismic imaging will be used for their research. So we will start with Alice, and she will be covering the modeling perspective.
Can you see my full screen?
Yes.
I can't see when yours. Okay, thanks. Okay, thank you. So Shusho asked me to talk about the modeling perspectives for this new seismic imaging experiment in central Chile. And first of all, I have to apologize. I caught COVID last week traveling. So if I say something a little bit mixed up, I'm sorry. Bear with me. On the title slide, I have 3 examples of modeling perspectives. The first one is an animation. Oh, let's start with this one. The first one, this is an animation of a fully coupled dynamic rupture, seismic wave propagation, acoustic wave propagation in a water layer, and tsunami generation simulation that is illustrating some of the multiphysics capacities we have if we're using high performance computing and better understanding the interaction of earthquakes and tsunami. The second animation is a dynamic rupture simulation for the 2004 Sumatra earthquake, which doesn't only model how this large earthquake is unzipping the megathrust, but also how co-seismically the megathrust is interacting with a set of splay faults here. And the third animation is stepping through 32 finite source models that are all data-driven. So these are inversions for the Tohoku Oki earthquake using the very dense and diverse data sets that have been recorded there. This is a way of comparing them by that we've been recently conducting by trying to find a common framework to upscale and to compare and to verify different source models, so to answer the question of what different arrays, for example, or different instrumentation can actually resolve in terms of co-seismic slip. This is a slide from the MCS, and unlike in the second last talk, MCS here stands for the Modeling Collaborative of Subduction. So this is one of the integrative working groups in SZ4D. Modeling enables, or we are an integrative working group because modeling enables knowledge transfer and crossing scales. And there's a couple of maps here. We're especially interested in coupled multi-scale models, but I do want to point out that models are really helpful for array design. So models connect observations across different space-time scales, can inform deployment of infrastructure, and allow us also to transfer whatever we will learn from based on observational insights from Chile to our high-risk domestic sites. Here, I highlight that it's the geology and the tectonics that determine also the physical processes that control megathrust dynamics and geohazards. And that is true not only in 2D, so not only in the cross-section sense, but also really in 3D, so including a long strike variability and also including, processes that connect whatever happens on the megathrust with our geologic context that's surrounding the megathrust. So for example, this is one example for Chile, where it's nicely shown that fault strength is influenced by the composition, or we know that fault strength is influenced by the composition of, for example, the incoming plate altered by underplating, as well as fluid release and pore pressure. And as I just said, long strike variability and segmentation is important. Another example, how geology and tectonics determine the physical processes that we're interested or that we are capable of modeling, is that along the variation in pore pressure and fault strength are controlled by geology, and forearc structure and sediments highly influence rupture behavior and tsunami genesis. Now, physics-based earthquake modeling can have many meanings or many realizations. A couple of them I highlight on this slide. We can look into wave propagation simulations. Wave propagation can mean seismic, acoustic, or tsunami wave. And we are now at the stage where we can really conduct those in a multiphysics sense. So for example, we can certainly go 3D and account for complex bathymetry. We can think in the seismic wave propagation part about including fully 3D physical anisotropy, poroelasticity. Nonlinearity is a big topic at the moment for better understanding nonlinear site response, and seismic acoustic coupling. Then there's dynamic rupture models, which means that we are not only solving the wave equation, but we are nonlinearly coupling wave propagation simulation to what happens at the source in terms of frictional failure of a fault. So this is the spontaneous dynamic earthquake rupture problem, solving for the nonlinear interaction of frictional failure and seismic wave propagation. Here's one example that illustrates that. And we have the seismic cycle simulation or modeling community, which is interested in rate and state friction-based simulations of the full seismic cycle, so covering thousands of years. And in this community, we are now at the stage of including complex geometry. So for example, one shallowly dipping main fault and several curved splays to better understand how they're interacting, not only co-seismically, but also in the interseismic periods. Very interesting in this community too is that we are now capable of including off-fault material heterogeneity. So for example, low velocity fault zones or rigidity variations. Now, if we're doing that at megathrust scale, we have to conduct simulations that are not only geometrically very complex, but they're also covering the long space and time scales that even a single earthquake is covering on these scales. So here's two examples. This is a visualization of SLAP 2.0 geometries as needed as dynamic rupture model input. And here's a recent snapshot of a study by James B. Miller et al. We have been looking into 2D seismic cycle modeling results with varying slab curvature and found that, you know, there's a difference between planar slabs that host larger, more uniform rupture cycles, while fault curvature induces stress and strength heterogeneity to enable a wider variety of slip behavior, more partial ruptures, and more variable space-time recurrence patterns. There's other groups that are reaching megathrust scale, sometimes simplifying the problem a little bit, for example, only looking at the uppermost 15 kilometers of the slab, or other model simplifications to make these simulations more efficient. The group of Shou Ma, group in Hong Kong by Hongfeng Yang. And there's also simulations using SPECFEM 3D. So this is a shout out to all the groups reaching megathrust scale in earthquake modeling. I just want to highlight a few things that we would be interested in better determining for Chile if we want to do these simulations in the SZ4D region. And one of them is related to a recent paper where we've been showing that it's regional factors that are important to understand not only rupture dynamics, but also tsunami generation dynamics. And these can be broken down into tectonic stress, depth-dependent variation in rigidity, and the yield strength of near-fault sediments. And this is a summary figure illustrating all these three regional variations and how they are important for governing megathrust dynamics and tsunami dynamics. I want to highlight rigidity. So these are dynamic rupture models outputs. So these are spontaneous propagating ruptures, and then we look at how fault slip develops, comparing a scenario which is accounting for a strong rigidity reduction in the shallow depth versus a standard PREM scenario. And you can see slip on the fault looks the same. However, rupture speed is very different, and also moment release is very different. And also important is that these models can be difficult to distinguish just from looking at them with seismic data. However, they have a large impact on tsunami generation. So for example, if we're accounting for not only the fault being governed by different rigidity or by different strength, but also accounting for either weaker or stronger sediments, we get very strong tsunami genesis trade-offs between slip to the trench, splay faulting, or bulk yielding of the accretional wedge. So if we account for weaker sediments, slip is pushed down dip. So we don't have slip all the way to the trench because the energy is used to yield the sediments. However, we get a much stronger tsunami amplitude in the coupled simulations. So if you're comparing a preferred scenario for the 2004 Sumatra earthquake with lithified sediments, a purely elastic material, and a weak sediment material, all three scenarios will capture a pronounced 2-peak characteristic of the tsunami wave. However, there's a strong agreement in this case of the stronger sediment case with the tsunami wave. It's not only these factors, but we also know that poor fluid pressure and splay faults are important specifically for tsunami genesis. So these are, this is a study by Madden et al., where we've been varying poor fluid pressure gradients with depth. And this is the output in terms of slip, peak slip rate, stress drop, and rupture speed for one scenario that has very close to lithostatic poor fluid pressure. That means the effective normal stress is almost constant with depth. And we see that the rupture dynamics are most realistic for such elevated poor fluid pressures. And the other part of the slide is a highlight of model that's linking a long-term geodynamic tectonic model of a generic subduction zone with several splay faults to a rupture model and a tsunami model, studying the effect of splay faults, including splay faults, gives several waves being generated by the tsunami, and it's not on the picture, but yields to much higher run-up at the coast. You can also see, if you look at this VP image here, that the geodynamic model, so this long-term subduction model, predicts very, very a strong VP difference here inside the accretional wedge. And also a lot of complexity in this splay faulting. We're only accounting for 6 splays here, but it would be certainly very interesting to also account for the antithetic splays in these models. So in general, we really observe in these models dueling dynamics of shallow deformation processes. And this is, I think, something where this experiment could really help us make important progress. Here's another example by Bimela et al., looking at actually the low angle normal fault in Papua New Guinea. in MAI, but the principle is the same. We expect the principle to be the same for a megathrust interacting with splays. So in this study, we have both splays and weak sediments, and we're finding really this dueling dynamics of what is deforming during co-seismic slip. So splay slip limits shallow detachment slip, but enhances and localizes subsidence. And synthetic shallowly dipping splays host more slip depending on the orientation, and they limit shallow detachment slip and enhance localized subsidence more effectively. As I said, we are able to now do fully coupled earthquake tsunami modeling, and that would be really interesting to set this up based on the findings that this experiment will reveal. The motivation for that is that one-way linking to the shallow water equations may omit tsunami dispersion, acoustic waves that might be interesting for tsunami early warning, especially on the Chilean side of things, and not only on the side and the other side of the trench, which is important for early warning, maybe in Hawaii and California. Momentum transfer and tsunami generation complexity. And to do this, we're coupling our rupture models with an extra layer that's representing the ocean. And then we can look at the interference of seismic, acoustic, and ocean Rayleigh waves and near source deformation that can be actually dominant in data recorded by offshore instruments that are being placed close to the source. And that opens a whole new set of models we can study. Here's a comparison of a classical linked tsunami that is just using the output of a rupture model to start the tsunami simulation, and a much more complex wave behavior in a fully coupled simulation. This is a snapshot. Now we're changing to Hoku after 32 finite fault models from 10 and diverse datasets that are running through in the first slide that we processed for consistent and realistic fault parameterization. So regardless the data set, we find that all models agree on the 64-kilometer scale features, yet they have substantial variability in smaller scale features. We do see large median slip in a median slip model of all models, and also high variability of slip near the trench. And there's much more detail in the preprint that I will link in the chat after I finish this short talk. And lastly, I want to highlight that recent developments in machine learning and AI also empower our modeling efforts, and they can be really useful in linking the data and the big data that's being produced in this experiment with modeling in an integrative way. And the goal would be to have a regionally data-rich and model-rich situation. So of course, ML data is useful for processing and denoising to analyze either real-time data or the data that is being collected, but we can also use these methods to reduce the cost of our forward simulations. So for example, we can build up surrogate models or reduced order models based on a few simulations or less simulations that we would need to cover a full parameter space of models and uncertainties that we want to explore. And this can, for example, be applied for evaluating models very rapidly, either in a rapid response setting, for example, to create shake maps in milliseconds, or, for example, if you're interested in uncertainty quantification and really need a large parameter space being covered. So in summary, as a modeling perspective for a new seismic imaging experiment in central Chile, our modelers are interested, of course. We can try to connect observations and also help to inform the deployment of that experiment. We know that the 3D, and that's important, the 3D geology tectonics determine the physical processes that control megathrust dynamics and geohazards. We talked about sediment strength, pore fluid pressure as very prominent examples, and just in general, the dueling dynamics of shallow deformation processes that can be helped to be untangled. That's not only important for shaking and tsunami, but also, of course, for dynamic triggering and how the megathrust would interact with the crustal faults overlying the megathrust. And lastly, there's a lot of potential in looking into machine learning AI approaches and compute-based high-performance computing approaches towards being data-rich and model-rich. And that's my 10-minute pitch. I'm happy for questions, and I will share some links in the chat.
Great. Thank you, Alice. I think considering the time, I would suggest that we save questions for the discussion and we can move to our next speaker. So we need to swap speakers due to some technical difficulties. So how about Damien? Are you here?
Yep, I'm here.
Yeah. Do you want to like share your screen?
I can do that. Yeah.
Thank you.
All right. All right, can folks see this? Cool. Okay. So yeah, I thought I would run through, I was asked to talk a little bit about what we might be able to do by integrating, say, seismic active source or other types of seismic imaging data with rock physics from the lab. Earlier today, I heard the idea that this session is kind of intended to think about the way in which seismic data might be useful to other disciplines. And I echo that, but also maybe flip it around and say there may also be ways that the data sets that can be collected in a complementary fashion could actually build on the interpretations or advance the interpretations of the seismic data by thinking about what else you can see besides velocity, for example, or geometry, and what that might mean about state variables or properties of the rocks that folks like Alice, for example, are really interested in. All right, and this is what I'm going to do is really just show kind of 4 very quick vignettes of work that I think highlight different ways that this might be done or ways that it could be useful. And this is work that a number of folks have done in my group, including Hiroko, which many of you know, Peter Miller, who's a grad student now at UT Austin, Josh Edgington, also a grad student, Andrew Gase, who is, I know, known by many folks here, and then this guy, Harold Tobin. All right, so the 4 examples, again, gonna kind of blow through these pretty quickly, but very happy to chat with folks offline or afterward by email or set up a call if there's more interest. The first is looking at an example from the Northern Hikurangi margin, where we can basically map, quantitatively map the water content of the sediments, and then push that a little bit further to not just map the water content, but think about the water budget and also parsing between bound fluid and interstitial porosity. Second example is thinking about porosity again, but more in the context of a strain budget and sort of combining porosity information obtained from P-wave velocity with balanced cross-section development to say something about the strain budget. The third is just a quick sort of hit that I think Laura Wallace, if she hasn't already talked about it, may talk about it a little later, is the importance of knowing those rock properties for the interpretation of geodetic data. And then finally, sort of a more complex example is, again, back to Japan and thinking about how we might use P-wave velocity information along with very careful and detailed information about rock deformation to try to estimate in situ stresses and pore pressure. Okay, so the first example, Northern Hikurangi, this is work that Andrew Gase did with Nathan and Xiao and others here. But one of the things that's quite notable about this margin is the subducting crust includes an oceanic plateau that's quite large, and that eruptive sequence at the top of the plateau has been heavily altered. And the result is that there's a kind of a mantle or a blanket that's up to a few kilometers thick on top of the subducting igneous basement, and is sort of part of the, quote, sedimentary section that's subducting, or the inputs. So it's kind of like this thick blanket that's subducting, and it's very low velocity. And so what's shown on the bottom left here is kind of a plot showing, back up here, is the sort of typical velocity of ocean crust on the right is sort of these blobs, which says Pacific plate and Indo-Australian plate. And then the observed kind of probability density of porosity or velocity versus depth within this layer, this mantle or blanket. And what we've done in this case is we've actually taken these velocities and mapped them very carefully to water content. And this is not porosity, but it's total water content using laboratory and drilling based information. And so this is kind of that conversion shown on the middle bottom of the slide here. And so sort of this non-linear and kind of interesting relationship that actually is well described by transforms of the form like those that Erickson and Gerard and others have developed, but calibrated for these materials. So then if we map that to water content, that's now replacing that bottom middle figure here. I'm looking for my cursor. It has disappeared, but that's okay. And so that bottom middle panel, you can see again, sort of the typical profile of water content in oceanic crust. And then you can see what the P wave velocities that are observed here indicate for that water content. It's really remarkable. So it's significant. It's on the order of 50% water content. So you can think of that as equivalent 50% porosity. And that's not at the seafloor. It says depth of 0, but that's actually at a depth of about 1 kilometer below the seabed. And it's the top of that particular layer, right? So this is still already deeply buried. And then you're down to several kilometers below the seafloor, and you're still at something like 20 weight percent, or sorry, rather 20 volume percent water content. So it's a significant amount of water. And then the other key thing here is that we also can combine laboratory-based compaction information, or sort of compression trend, with that observed total water content. And that's what's shown here. And so just to lead you through this, just again, sort of pushing this as far as we can right now. So the green curves are the total water content versus depth for 2 different kind of terrains beneath cinder cones and in the basins of that layer. The orange curves are compression behavior defined by laboratory and drilling information. And then the blue is essentially what would have to be left over as bound water in the minerals. And the reason that this is important is to be able to parse this, if you can push it this far, is that the rate and time and PT conditions where then you might project this water coming out is very different if it's compaction driven or dehydration driven. And so being able to actually put numbers on these budgets is kind of cool. All right, so that's sort of example number 1, and that's in some ways the lengthiest example. As I said, I'm going to kind of race through this. Example 2 is from the Nankai margin. This is work that Greg Moore and his student Melody Studer did, along with myself and a few others. And here off the eastern coast of Shikoku Island, the so-called Moroto transect, which is the site of a bunch of ODP drilling in the 1990s and 2000s. And there's a 3D seismic survey that was also conducted there many years ago. Greg and his student conducted a balanced cross-section to define essentially the shortening in the outer part of the wedge. What was cool about this particular study is, again, mapping from P wave velocity to porosity allowed us to not just quantify a slip on the faults themselves, but also to quantify the shortening resulting from the ductile compaction or the porosity loss. And it turns out that porosity loss, as you can see from these numbers up here, is actually the majority of the shortening. So it's not like rigid blocks sliding on faults, but significant shortening is occurring because of that compaction. And the way you can get at that number and quantify it is, again, through P wave velocity, and it's changes as a function of distance from the trench, and accounting for that in the cross section. And so then the sort of final piece of this is, if you know that there's shortening in the upper plate, at the same time we know that the lower plate is essentially trucking down at the subduction rate or the plate velocity, then what we really care about, if we think about, say, the potential for locking or the slip rate on the master detachment, the décollement, aka the plate interface, it's really the difference between these 2 vectors. And so the more permanent strain or permanent deformation you have in the upper plate, the less slip you actually have across the fault. And so that's what's shown in the lower panel, is really just zooming way in on that outer, in this case, 7 kilometers where this cross section was done, that in the outermost part of this system, actually there's almost net 0 slip across the décollement. Everything is moving together because you're accordioning or shortening the upper plate. And then as that sort of stacks up and that strain progresses, you begin to recover something like 35% or 36% of the plate rate when you're back at about 7 kilometers from the trench. But this, of course, means that it's something to think about, not just in terms of the strain budget, but ultimately when thinking about geodetic data. When we see shortening or strain, is it permanent and inelastic, or is it something that might be recovered in an event? What is the net amount of slip or the cumulative slip on the plate interface? All those things can be essentially deduced from some quantification of this strain budget. All right, third example is only 1 slide. Here it is. It's just a reminder that also in thinking about interpretation of geodetic data, one of the other things that's super important, and Laura again may talk about this, is not just the geometry, but also the elastic properties. And in particular, gradients in the elastic properties of the material have a profound effect on what you might think you need for slip or locking to generate a particular signal that you observe. And so what's shown in the bottom panel is an example from the Nankai system off of the Kumano transect. So this is the anthracized sort of really heavily populated drilling transect over the last 20 years, 15 to 20 years. And so what's shown are the open circles are the strain that you would predict for a slip patch somewhere on the interface. Or if you wanted to think about it, that could also be, if you locked it, it would be an equivalent kind of signal for a unit amount of slip. So those are the open circles for sort of traditional homogeneous half-space models. And then the closed circles are what you would see for strain in the case of realistic elastic properties. And in some cases, you're talking about something like a half to maybe only a third of the signal. And so what this means is that if you're inverting geodetic data, whether it's strain or horizontal displacements or vertical displacements, you might significantly underpredict the amount of locking or slip that you would need in this particular case to get the observed signal. And so that's not to say let's drill in, no pun intended, to detail in this particular margin, but just to say that this is, again, something that can have not just sort of, a 30% kind of number impact, but threefold in some cases kind of impact on how you interpret geodetic data. And so potentially very important. And for this, really what's needed is not just P-wave velocity, but in thinking about survey design, really to do this properly, you need P-wave, S-wave if you can get it, and density information, which could be inferred from P-wave through a transform to porosity, for example. All right, and then finally, this is one that's a little bit of an older example, but just to throw it out there, I think folks often try to do this, and it's been done in a number of margins, is to take something like velocity information and you don't want to just map it to porosity. I mean, that's neat. But ultimately, the reason we care about porosity, or at least one reason we care about porosity, is to then try to infer from that effective stress state and pore fluid pressure. And this is certainly possible, but it is not easily done with generic information about sediments globally that tell you how porosity is related to stress. Really, to do this, you need to know the constitutive behavior of the materials of interest, and that's lithologically dependent, as well as other texturally dependent, initial condition dependent. And so we've done this just as a sort of case study, also in Nankai. This is again off the Key Peninsula here. So this is that anthracized drilling transect. And then here are just two examples of what those low velocity zones look like. Sort of this bluish lozenge that extends down to about 45 kilometers landward of the trench, down to depths of about 7 to 9 kilometers. And so we do this by conducting experiments in the laboratory to measure P-wave and S-wave velocities as a function of stress path and porosity. And this allows us to map P-wave to porosity, which does not depend. So all these different colors are different stress paths. And so to first order, P-wave velocity doesn't care how you got there. All it cares about is what is the porosity. So that's very helpful and sort of simplifies the problem. However, porosity does care how you got there. And so the stress state for different for a given porosity, and here's porosity on the y-axis, sort of a proxy for that is void ratio. For example, if you're at a condition that's near shear failure, which is this blue line, so-called critical state, then for a given mean stress, you actually have a much lower porosity. And this is because you get shear enhanced compaction. And so this is important because you need to know which of these curves you lie on if you're going to map between the observable or the inferred value from P-wave velocity, say porosity, to something about stress. In the case of the upper plate at Nankai, what we've done is assumed, for a variety of reasons, that we are on or close to this critical state. In other words, we're at a condition near the shear failure of the material. And when we do that, then we actually can quantify an upper bound on the pore fluid pressure and the horizontal maximum stress. And so that's what's shown on the upper panel. And this is work that Hiroko did as part of postdoc in 2012. And so it basically shows that this low velocity does indeed appear to correspond to elevated pore fluid pressure and low stress. Again, this is sort of an upper bound on that because we've assumed that maximum case of shear enhanced compaction. And so it could be a little bit lower than that, I suppose, but that's sort of our best guess. All right, and so just to wrap up, again, sort of four key ways that, again, I think there's some really cool connections here. One is tackling the question of fluid budgets. A second is, well known to this group, I think, is the ability to say something quantitative about physical properties, and that's valuable for a lot of different reasons. The third is the interpretation of strain and geodetic data is for two reasons. One is that permanent compactive strain, but then also the role of that heterogeneity and elastic properties is really important. And ultimately, this might actually be super valuable if the timing works if a survey happens off of Chile, to be able to use that kind of information for modeling and to actually plan the siting of geodetic stations that go offshore, which would be really valuable. And then finally, there's a little asterisk here, is that there are potential applications to quantify stress and pore pressure. Kind of requires you have a lot more detailed information about the constitutive behavior of the materials, but it's certainly possible and is in a lot of ways kind of a holy grail here. And so I'll leave it there. And I probably don't have time for questions, but.
Great. Thank you very much, Damien. I think we probably, it's better to move on to the next speaker, and we can save questions at the end of the session. So the next talk will be given by Donna on behalf of Christine Moreau to give us a perspective from landscape and seascape.
All right, Damien, can you stop sharing your screen? Thank you. I'm already going to do a bad job of giving Kristen's talk. I don't think I need to also re-give yours poorly. All right, can everyone see and hear me okay? So this is a big thank you to Kristen Morel, who put together some slides about how seismic imaging can be used to provide useful information for some of the landscape and seascape questions. And she sent these slides, and I'm going to very quickly try to go through them and summarize them. But I apologize to her and to you that she's not here to give this talk. So some of the goals of landscapes and seascapes that are kind of most pertinent to offshore seismic imaging, or kind of some needs that are most pertinent to seismic imaging, are that they really require offshore stratigraphy to kind of extend our records of geohazards further back in time. So deposits from mass transport deposits, earthquakes, storms, floods, eruptions. And they also have a need to kind of understand what's controlling the whole transport of sediment from onshore to offshore. And so the kind of structural and depositional framework provided by imaging would be really valuable for Chile. And so, as she says here in this sort of second part, seismic imaging can give us the geometry of offshore sediment deposits that record basin scale depositional patterns. They can also provide one piece of information towards the frequency and extent of sediment gravity flow deposits, which give an insight into geohazard activity in deeper time, and also give offshore stratigraphy to highlight changes in climate and past depositional environments. And so to kind of illustrate what seismic imaging might be able to do for LNS, Kristen included a couple of examples from Cascadia. And so here, these are from southern Cascadia, as you can see from the inset here. And so the lower image shows a kind of a cartoon based on seismic reflection imaging, and emphasizes that seismic reflection data can give us the broader tectonic context and geometries that can help us understand and contextualize sediment transport. So here we can see the faults in the forearc, the overall thickness and geometry of the forearc basin, changes in the composition of the forearc crust can be revealed that are one potential control on this sedimentary system. In more detail, if we look at the upper panel here, this is a higher resolution imaging, as you can see. These imaging data can show us the details of the geometry of this forearc basin, and including how we have this thickening of sediments back towards land, potentially controlled by a fault system, and also kind of temporal changes in sediment delivery to the forearc with a really, for example, a regionally extensive Holocene layer, which is illustrated here. As kind of another example from this forearc basin, seismic imaging data have also been used to inform and understand core data, to kind of look at have a deeper time perspective of multiple kind of you can see of these multiple deposits. Maybe I can go to the next slide here, but in this imaging example, we see kind of a series of mass transport deposits that have been kind of imaged seismically, but then especially with integrating with coring data, and cores that were located based on the seismic imaging data can kind of have a chance to track this, the sedimentary system and understand how things worked with time. And so for the kind of Chilean case, what Kristen has highlighted is that, we have some knowledge already of, shallow and active structures in the forearc from kind of bathymetric and seismic data located, close to land up on the shelf. In this example, showing this particular canyon system. And so this gives us a context for both active deformation and sediment transport. And so kind of an opportunity could be that these seismic reflection data could help us, understand, the offshore sedimentary transport systems, kind of what is the fate of sediments that are eroded and carried across the landscape for, where is their fate in the seascape. We can identify marker beds to correlate with horizons and existing legacy data, so build kind of a more regional framework across the area to look at the geometry and evolution of offshore sedimentation. It could be used for targeting sediment coring and dating. And ideally, some of the seismic work should be located offshore of the surf array. So this is sort of showing a conceptualization of onshore monitoring of active surface processes. And so having seismic imaging data offshore from that would allow an extra context for the surf array. And this is again kind of illustrated here in these figures. And so I'm going to stop there. I just wanted to quickly review what Kristen shared with us. I'll put her slides in the drive, but hopefully that at least quickly introduces some of the ideas that she shared, although not nearly as well or eloquently as she would have done it.
Thank you so much, Donna, for presenting Kristen's slides, and also for catching up with our delay. And now, I think we're closer to the schedule. So how about we move on to the next speaker? Laura, are you here?
Yeah, can you hear me?
Yes, we hear you fine. Great.
Okay, I'm having technical problems, so I'm basically going to use my iPhone as a microphone. And Shosho, if you can show my slides or somebody, it's in the drive, okay. And I'll ask you. My microphone on my laptop has decided to bite the dust, so
I can do that if you like, Shosho. I think I have them here.
Oh, okay, yeah. If Donna, you can share Laura's slide, that would be great. Thank you.
Cool. Thank you. And there's a fair bit of overlap. I guess Damien wants to be a geodesist now. He talked a lot about geodesy, so you'll hear a few messages repeated in my talk. Okay, so I'm going to talk about some of the, at least from my experience at other margins and other, studies, what other studies have shown in terms of a lot of the benefits that can come from an active source experiment in a place like Chile for geodetic investigations. Next slide, please. Okay, so this is just stuff that you guys really probably all know, but obviously we're using geodetic techniques to measure surface deformation response to plate boundary processes, and particularly at subduction zones. We can, detect strain accumulation due to interseismic coupling on the megathrust, transient events, slow slip events, also co-seismic deformation and post-seismic processes. And onshore, these sort of techniques are very mature and have been used for many decades, and we have very high precision. And so those onshore methods are really good for seeing processes on the deeper end of the seismogenic zone and down dip of the seismogenic zone. But the offshore area is really the emerging area where there's a really big blind spot, and is really very important for the offshore Chile region, because much of that sort of area of interest of the subduction zone, particularly the earthquake generating part, is of course offshore. So the main techniques we tend to use are GPS acoustic to detect horizontal displacements, seafloor pressure sensors to detect vertical displacements, particularly in transient events. And then for strain, you have the borehole observatories. Damien mentioned the ones in Nankai. There's also several other subduction zones that have those, and we can detect volumetric strain, and then direct path ranging, which also allows you to detect strain over short baselines. Next slide. Okay, so I think from a geodesy point of view, one of the most important things that could you guys could produce that could really help us is kind of obvious, and it's really defining the geometry of the faults offshore that are responsible for the deformation signals that we would be observing geodetically. So particularly the subduction megathrust is very important, but also any major splay faults that you image. So we need these to basically invert for slip on these sources from our surface deformation fields. So that would be great. I would really encourage, if you guys do this experiment, if you could also develop some kind of offshore community fault model out of it that geodesists can then draw on for their efforts when there's eventually seafloor geodetic data out there. And then also these types of things are going to be very, very useful for design of future geodetic experiments, to do resolution testing and other types of things. You need accurate, reasonable fault geometries. And for example, if people are interested in targeting splay faults, an idea of what are the splay faults that you think are the most active, what's the geometry of those things would really help. Okay, next slide, please. The other thing, and Damien touched on this a little bit, but there's also a real need for a comprehensive seismic velocity model, because we now know, particularly at subduction zones, we can't just assume that the Earth is kind of a uniform elastic half space, which is what is commonly assumed in most geodetic studies. The really strong contrast and elastic properties between the overriding plate and the subducting slab really have a very large influence on the resulting deformation field. And for example, for offshore slow slip events in New Zealand, we've shown that this can result in a 40% increase in the magnitude of slip in the slip models to fit the surface geodetic data. And also, as Damien mentioned, with the borehole observatory data, this is even more important because those near surface elastic properties, particularly where the boreholes are located, we need to know those very well to do any reasonable deformation modeling, because this can impact the results in terms of the slip amounts by several fold. They've seen that in Nankai, and we've also seen that in New Zealand. So I think another request, if you guys do this experiment, if you could develop a community seismic velocity model, that would be greatly appreciated, I think, by geodesists, but also by many others that would use this type of thing as well. Next slide. And then another issue that I think is going to be really important to look at is thinking about what are the stressing rates out near the trench. And that, again, similar to the surface deformation, is going to be very strongly influenced by the elastic properties and the shear moduli of the material surrounding the fault zone. And this is, this figure on the right is just a preliminary model that we did for a recent proposal comparing stressing rates out towards the trench. So that's out to the right, from a uniform crustal rigidity model compared to one with realistic crustal rigidities, and you get 10 to 100 times lower stressing rates. This is shown in terms of kilopascals per year with realistic rigidities. So, for example, if we want to assess the possible extent of stress shadows that have postulated to exist up dip of these locked seismogenic zones, we really need to be taking into consideration the real Earth properties and not just use uniform elastic models. Next slide, please. One of the other, so in New Zealand, I'm really going to focus on New Zealand examples for this because obviously I'm most familiar with that, but also we've got really high quality active source seismic imaging there. And then we've also had a number of seafloor geodetic experiments with which we can use to compare the physical properties observed with the active source experiments and then the slip behaviors that we observed geodetically. And we found in New Zealand that, to really get a handle on what are the physical processes that are responsible for, say, locking on the subduction megathrust versus slow slip and creep, having really good imaging of the structure and physical properties is absolutely critical. And, you know, on the left, we see Andrew Gaze showed really nicely that we've got sediment subducting in the area of strong locking at the Hikurangi margin, whereas further north, where we have mostly creep, there's not as much sediment subduction, and that's probably influencing the distribution of interseismic coupling. And likewise, at northern Hikurangi, seamounts and subducting sediments are really strongly influencing the distribution of shallow, slow slip that we've observed there. That's been shown and really in several papers in the last several years. So to put this into context and to get a handle on the physical processes behind what we observe geodetically, we really need good imaging. It's critical. Next slide. And then finally, I think that the imaging could actually give us a really nice guide to help design future geodetic experiments. For example, you know, we often see really interesting things happening geodetically in terms of either slow slip events or transitions from locking to creeping in areas where there's a lot of heterogeneity in the structure and the physical properties of the offshore margin, both in the along strike direction and in the down dip direction. And I think that, you know, having much more context in terms of the imaging of the structure and the seismic properties could provide a really useful guide for where targeted geodetic observations would be most valuable, because you guys are still dealing with a really big piece of real estate and some narrowing down is going to have to be done. So I think that could provide some valuable context. So next slide. And then finally, I guess my titles on my thing are not working, but this is the title for this slide is supposed to, I don't know if you guys are considering a passive seismic, go back to that, thanks. A passive seismic component to this experiment, but I would definitely encourage that. I think it would be really complementary, and it would also help to provide a lot of things that we need from a geodetic standpoint and also from other standpoints. So the velocity, you know, for the elastic property constraints, VP is really important, but so is VS. And I think from what I understand, VS is easier to get with a passive deployment. And then also detecting things like tremor and low frequency earthquakes. And Sergio mentioned the swarms, which, you know, things which could be diagnostic of episodic slow slip events. You know, if we can detect where these things are happening out there, that could also help guide design of future seafloor geodetic deployments in a much more informed way than what, you know, is currently possible right now, given a lot of the knowledge gaps out there. Yeah, and then I think also a better knowledge of the offshore seismicity distributions, thinking in terms of locking versus creep, could also help inform future design. So a passive component, I think, would be really nice if you're thinking about it. Next slide. And that's it. So I just really, yeah, just kind of want to emphasize the active and passive seismic data provide some really critical information that's needed for robust interpretation of offshore geodetic data in particular, including the fault geometries and the elastic properties. Imaging provides really critical context for interpreting this, what the origin of these slip processes that we observe are. And I also think this experiment could really help to reveal some promising targets for future seafloor geodetic and seismic deployments. Thanks.
Thank you so much, Laura. This is great. So now I think we can have a question session for all the speakers who have presented in this part 2 of the session. If you have questions for any of the speakers, you can either type in the chat box or raise your hand and can ask your questions. It looks like it's all clear. Okay. Jim? Jim, can you ask your question?
Sorry,
Hi.
My computer seems to be slow coming online. I hope you can hear me. It feels like both Alice and Laura kind of emphasized the importance of improved rigidity models or improved velocity models or strength models for the kinds of modeling they do. And I'm curious about the relative importance, I assume it's both, but I wanted to ask, of the upper plate versus the lower plate in both of those scenarios, and the degree to which we're having accurate velocity information of both of those systems is important or not for the kinds of modeling that you're doing.
Laura, do you want to go first?
I can go first, sure. I'm complicated today. I mean, I think the upper plate is, the subducting plate. I don't think the velocity variations are going to be so massive that I think if we have a kind of broad, rough idea of those velocities, it's good. It's really kind of getting a handle on for the geodesy, the contrast between the upper plate and the lower plate. That has a big influence on the slip models with the surface geodetic data. And I think also, getting a handle. I think the upper plate's probably more important, is my instinct with that for the geodetic stuff, and particularly because there's going to be more variation in that as you get into the near surface and things like that.
Right, it's a similar answer for us. I think we're really interested in the upper plate because the contrast is so large. I guess that's the answer. We have just a much less constraints, and the potential of missing important information that is really governing dynamics of what we're modeling is much larger for the upper plate. But we are interested in the properties of the downgoing plate as well, of the downgoing material as well. Specifically, if we do have strong bimaterial contrast, or even small bimaterial contrast, we know that this can affect rupture dynamics of a megathrust earthquake a lot. We don't know yet how much that affects slow slip or other like aseismic processes, but it's certainly really interesting from the physics point of view to look more into these contrasts. So it's a very similar answer. For tsunami generation, I think there's a strong focus on the upper plate, obviously.
Thank you.
Ignacio, you had your hand up. Do you still have a question?
Yeah, it was kind of related, that question for Laura, but maybe I would like to ask you about the passive imaging in terms of advantage and disadvantage. I would think that is cheaper than the active one, but you have less control, right? And you have more uncertainties.
Who is that question for?
Okay, again, no, because you were talking about passive imaging in your presentation.
Yeah. So I think, and I'm not a seismologist, so I'm just talking out of my whatever. But my understanding is that VS is kind of hard to get with active source, and we need VP and VS ideally. So that in terms of but a seismologist should talk about pros and cons of passive.
Yeah, because
versus
I'm
active.
thinking if we are interested in the upper plate, for example, for tsunami generation, as Alice was saying, maybe we have extra data and we can try to come up with a cheap alternative to try to increase with passive sources and try to increase the data with them. Yeah. Thank you.
All right, I have a question for both Laura and Alice. So you both kind of mentioned about this 3D like velocity structure or like or 3D modeling, and as you know, we plan to have like 2D lines, pretty sparse 2D lines. So I'm wondering, like, for your work, for this third dimension, what is the resolution that is important for to guiding our experiment? How closely spacing those are in order to be like suitable for your modeling or like your geodetic work?
I have COVID, you go first.
I'm technologically handicapped though. Yeah, I mean, it's hard to know. It depends on, you know, the density of geodetic data that you have to fit. If you've got more data, you want, you know, obviously higher resolution model. If you're dealing with the borehole observatory data, you really do need quite high quality. So you'd probably want to site borehole observatories on a really nice, well-constrained 2D line in terms of getting that. So it really just depends a bit on the kind of distribution of the data you have. For the surface deformation data, I think, you know, it doesn't have to be crazy detailed, but I think that would maybe be, to make that a more of a 3D type of thing is maybe something where I think it could argue for integration with a passive deployment, maybe a grid of sites spanning at least some of the area that you guys are going to be doing the active source imaging. But yeah.
Yeah, it's from my side, it's also it's a tricky question. So, you know, when we're setting up these models, the length scales that the models are sensitive to are governed by physical processes that happen on relatively small length scales. So we're talking about I don't know, maybe 250 meters or less, you know, like really relatively small on the megathrust scale. However, it's not clear that this variability on this tens or hundreds of meter scale is really important if you're interested in hazard of big earthquakes, for example. So it depends a little bit on the specific modeling question or research question you're interested in. Anything we can get, I think, even if it's kind of a 3-segment variability, you know, like simple Cascadia, and you have north-south and the middle part, which is different, that would already be interesting. Yeah, if you have my wish list, it would be everything on a 500 meter scale, but I think yeah, anything that informs us about variability and to motivates also modelers to go beyond the 2D, simple 2D transaction would be useful, I think. Yeah.
Great, thank you. 500 meters is a little bit hard to achieve, but I think our survey may be the first step towards that goal. So we will do one more question, and then we will have 5 minutes per, like a break, and then we will have the discussion session. So Manel Prada, could you ask your question?
Yeah, can you hear me?
Yes.
You can't see me because I have the other webcam. Sorry. You can see my back. Hold on a second. Perhaps this one. It's the first time I'm using this webcam. Anyway, you can hear me. Yeah, the thing is that what I wanted to say is regarding this. There you go. Hello. Yeah, so very nice talks today. I just want to thank all the speakers. And what I wanted to say is regarding this 3D survey. I know you intend to acquire 2D sections, but a possibility would be to deploy OBS, an array of OBSs for a passive experiment, as Laura was suggesting, and leave them there while you're shooting. Now, the shooting spacing would be very important and will probably will define or determine the spacing of anomalies that you will be able to resolve with your tomographic method. So I'm just dropping an idea there. You could perhaps do some synthetic tests before with different OBS spacing and shooting spacing, assuming different heterogeneities in the velocity field of the upper plate and the roughness of the interplate. And then you would come up with a set of models that you would probably just play with and design your experiment in order to be able to actually image specific things if you know what you want to see. So yeah, I think synthetics will actually help a lot before designing this thing, and using OBS's plus the 2D seismic sections. I think they will provide a lot of insights in that. Yeah, that's it. Just this comment.
Great. Thank you so much for your comment now. So now let's take a 5-minute break. And then now it's I think 10:18. All right, we're back at 10:23, and we will have breakout groups discussion and to discuss some of the questions related to today's talk. And I think we now have 45 people. Like maybe we can do 3 breakout groups, or I think 4 is fine too. Our original plan is to do 4. I think if we are like around 40, we can go with the original plan, or like we can also do 3. All right, great. Okay, now let's first take the break, and then like we'll decide how many groups we have after we're back. Thank you. So Donna, I think we will combine 1 and 2 and 3 and 4, right?
Sounds good. I think that's the right way to go.
Great. So
Okay,
we
so
now have
I'm going to assign everyone automatically into 2 breakout rooms, and then I will reshuffle to make sure that breakout leaders are in the correct rooms, but please be patient.
Sure. Did you need to say anything to introduce breakouts first before we send people away?
Yes, thank you for a reminder. I almost forgot. So I do have a list of the topics that we will discuss during the breakout groups. I will quickly share my slide, and just bear with me. Okay, share screen.
Bye.
Can you see my slides now?
Yes.
And I'm not sure if I need to swap my display, maybe this way. Anyway, I think so for the breakout session, like the original plan is 40 minutes, but now like let's just shorten this to 20 minutes. And we will also combine groups. We will combine group 1 and group 2, and then we will combine group 3 and group 4. And so Andrew will be the scribe for the new group 1, and Brandon will be the scribe for the new group 2, and Hannah will be the scribe for the report back session. So we will have, so let's do like 20 minutes breakouts, and then like we will be back to the main room at 10:45 and to do a quick report back and summary. And so like each group will have like document for the instruction, and we will also have a Jamboard to everyone can draw or write to discuss the line design. And just want to remind everyone the ground rule to like raise hand to speak, and try to limit your speaking time, especially now like we are really tight on our schedule, and everyone's view is valued. And for international participants, if you find it is easier to write down your comments or ideas in Spanish in the Google Doc, please feel free to do so. So for the breakout sessions, this is the original plan, but now like due to limited time, I think we may not have time to go around the room to introduce everyone. Like we would, this is a 2 parts of the discussion. One is to follow the part 2 of the talk session to discuss the integration of active source seismic imaging with other studies in subduction zone research. And questions include, how would active source imaging be used for your research, and what data products would you need, and what resolution would you need for your work? And also, if you want to use active source data, what data format would you make it easiest for you to use that to incorporate the data in your work? And then the second part, we will discuss the imaging target. So like each group can cover like all 4 themes: the subduction input, megathrust, upper plate faults, and sediment transportation processes. So we would like to know which specific geological area of central Chile would be good for future detailed seismic imaging in order to help address SZ4D science questions, and also to facilitate comparison with the 2 domestic subduction zones, Cascadia and Alaska. And also where would the velocity constraints from OBS data would be most useful, because we will only have a few lines for OBS lines. And then like what specific structure or seismic properties would be most useful for to address your scientific questions. And then if there are active source seismologists in the room, we would like to hear from you based on your past experience with imaging Chilean margin or other subduction zones. Do you have any suggestions for the survey design? Following the breakout group, we will have a 15 minutes quick summary, and then like those ideas and discussion points from this workshop will be synthesis to help us prepare a proposal to be submitted to NSF in the spring of 2024. We will also write up a short report to be published in the next SZ4D newsletter. Okay, that's all from me. Thank you. So now, Anais, could you assign us to the breakout groups?
Sure. So first assigning randomly the participants, and then I will assign the co-host. Okay. Now I'm assigning the co-host.
Okay, great. Thanks.
Hi, Donna.
How are you? Oh, bye.
1 and 4, right? This is 1 and 4.
Yeah, I think 1 and 2 together and 3 and 4 together. So
you are.
I think I'm 1.
You are 1 and 4.
think I'm 2, so
We'll see where we land.
Moving my way. Just be patient, please. I'm
So thank you so much, Anais. Thank you.
Sorry.
Brendan is going to
1, 2,
Jacob.
3, 4.
Nathan. Into Eduardo. Oops. Donna. 1. Jacob. 2.
Just Dietrich was just talking while everyone in our group was brought back to the main room. And Donna, I do not know if like there is some topic that like you want to further discuss a little bit here, or I think for our group we would like to hear the rest of what Dietrich wants to say, because it's just right in the middle of what he was saying.
That would be great to hear the rest of their thought. And then
I make it short. I was just saying, okay, there's so many options, but one is, I think, if the size is somehow comparable to Alaska Array or somehow, because there's always limited things. And considering that there's a lens, I think it should not be an offshore part as well, and onshore should work nicely together. I think this one, there was one figure was showing this place south of Copiapó. I think that's not too bad. I think north of Copiapó, we've been just there with the cruise, but still there's no good MCS streamer data beside of Ceviche.
Exactly.
Yeah. And there's one thing from a seismologist standpoint, I think I would densify the seismological station significantly more than in Alaska, because there's already a number of offshore deployments in Chile, especially when it comes close to the trench. I would densify this more than Alaska. That's it.
Great, thanks for the comment. So now, how about like we hear a quick summary from both Brendan and Andrew of the discussion?
Sure, yeah, I can go. Ours was pretty short. But yeah, some of the things that we talked about, the imaging targets that were mentioned were the Juan Fernandez Ridge, for the obvious reasons that were mentioned in the presentations before, seismicity and it being a barrier to sedimentation patterns along the margin, and also the Challenger fracture zone being an important site that could have anomalous properties potentially in the downgoing plate as well. There was some discussion about what opportunities there might be to link with other sorts of complementary data sets, and in terms of the experiment, potentially with electromagnetic imaging in the offshore domain, and the desire to think more about these other data types and how they might be integrated. There was mention about the 2D reflection data and how this this Chilean part of the margin is very big, and with sparse 2D data, you can always capture the complexity. So there was some mentions of trying to make use of the existing data sets, maybe in terms of reprocessing or designing some along strike lines in this experiment to tie those together and to better integrate with the newer lines that are collected. So basically capturing the existing data. And along the same lines, about integrating active and passive source data sets. So one of the key targets being the geometry and depth of the plate interface, and having an onshore offshore component to the experiment would help extend imaging on land to greater slab depths, and the offshore constraints would be very useful for passive seismology in terms of earthquake relocations and integrating into tomography models as well. And that's all I have.
Great, thank you very much, Brendan.
I'm realizing I think we spoke about a lot of the same things. So in our group, The first discussion was about complementary EM and how it's often helpful to have MCS data and also wide-angle seismic data in the same place that you could have maybe controlled source EM or magnetotellurics. And so if any future studies happen, they should probably be designed complementarily. There was some discussion of shear waves, which have been recovered well on the incoming plate around 43 degrees south. And there's some question as to whether or not they could be recovered on the incoming plate within this survey area. Or we also discussed whether or not it'd be possible to recover them on the upper plate, although we seem to be a bit more skeptical about that. And then we focused a lot of our discussion on the survey design, what's a reasonable number of MCS lines, whether they should be evenly spaced or more focused in certain areas. And there was some discussion about the major change in accretion versus erosion going from south to north, and whether or not the survey should be densified across that transition. We also spoke about the along strike lines. There aren't any, at least to my knowledge or our group's knowledge, any very long offset refraction profiles that go along the incoming plate or across the forearc. And so that would be of interest. And then also you heard what Dietrich was speaking about when we broke. So that's everything.
Great. Thank you, Andrew. Yeah, it looks like there are like some overlaps in the two groups discussion. Like I heard like the mentioning of the Juan Fernandez Ridge for in both groups and their importance as a segment boundary, both for the segment erosion and whether it's erosion or accretion, and it looks like, and also like Laura mentioned, its importance in the from the geodetic perspective. It looks like that maybe like one target to densify the lines like on top of our semi-regular spacing. And another question, like I think I want to hear from all of you. Like we have mentioned about this velocity constraints from OBS data, like basically how many lines we will need for with the OBS deployment. Like we have heard from Andrew's summary, like it looks like we want a long strike line with the OBSs, and this will certainly impact the design of the survey, like how many OBSs will we deploy and whether we have it as one leg or two legs of the cruise. So I want to get people's sense of, like, in terms of dip lines, we currently are planning like 4 of the dip lines with the onshore extension. And so like it's 4 lines, like currently at regularly relatively regular spacing. Is 4 lines enough, or like should have more, or now?
Yeah, just wanted to say that if you have a specific objectives already, some locations have already popped up here in the discussion. I would go for a 3D instead of 2D. I mean, you can shoot 2D MCS lines, okay, to get some controls on the tectonic structure. But while you are shooting these 2D lines, you could have an array of OBSs sitting on top of these specific targets, recording these 2D lines. And in the end, you would have a pseudo 3D, and you would be able to capture a long strike and down dip velocity variations and potentially geometrical variations of the interplate. I'm just thinking about the Esmeraldas surveys. I don't know if many of you have heard about this, but well, it's an array of OBSs that was deployed in offshore Ecuador, and it was an experiment to capture velocity variations of the subduction zone and the interplate. And I'm thinking about this, but at smaller scales on top of these specific targets. Otherwise, I don't know how many lines. I mean, it would depend on the target that you want to address during the survey. But if you have bigger places, then I would go certainly for a 3D. OBS array.
I think one of our challenges is that it's such a large area of the margin across which we wish to provide some backbone constraint. So I think were we to go in a direction like that, we'd have to be quite strategic about choosing a place to have that within the broader footprint. Yeah, but you're absolutely right. That's obviously what one would want. That's challenging.
Yeah. I mean, the area is very long, so you won't be able to deploy an entire array there. So you should be quite careful where you put your instruments. Yeah.
Bertrand, you want to?
Yeah, just to build up on what was just said. It's a very, very good idea what Manel said. I come from the modeling, and from modeling point of view, the 3D makes way more sense than 2D. One thing we have done in a very different context, but it may apply here, is that you can have an hybrid thing. You can have a backbone of stations of OBSs that do not move, a few OBSs that do not move, and also do the lines. It's you can do an hybrid thing between the two. It's better than just having lines usually.
Hey, thanks for your comment. So John Collins is here. So I want to ask a question to John. So we have talked before, and I believe like around 70 short period OBSs will be available around our ideal time window for this experiment, which will be late 2025, early 2026. So John, like I do not know if you have more updates on maybe the availability of more OBSs, either short period or broadband in that time window. Maybe he is not like wrong. Okay, so there's some discussion in the chat box. Active source imaging. Yeah, so people have been talking about this integration of active and passive source. I was thinking for the passive array, it's like Donna, you may be able to answer that. I thought that is also part of this phase 2, like planning, right? For has a large backbone array, passive array. Is that right?
It's definitely the case that the intention of mega array ultimately is to characterize subduction zone behavior, and there's been a lot of discussion about what maybe what for any of the arrays of SZ4D, what kind of pilot studies might be needed to figure out how to design the full implementation of mega array. And so I think that, you know, a targeted OBS deployment to plan for that could make a lot of sense. I think what we'll have to figure out is how to strategize what goes in what proposal. I think we were motivated by this experiment, and that we kind of have one window to propose an active source seismic imaging experiment over this area before the Langseth is retired, and while we have those capabilities. And so that's been a bit of our priority. Of course, it would be good to have and coordinate with all of the other things. And so something we can kind of consider together as we move forward is like what goes in this proposal. Maybe this proposal could motivate another proposal to add on and complement what we're doing here. So anyway, I think it's something that our community has to continue, all of us, to discuss how we can get everything done that we think should be done to do the best study we can. So, but I think we're coming to the end of our time, and we appreciate everyone taking 3 hours to discuss about this. Obviously, 3 hours was not enough for everything we want to say to each other and talk about. But so I think that maybe after this call with Shosho and Nathan and Eduardo, we can talk about how to follow up and seek more other mechanisms to ask for your feedback and ideas after this call, in addition to what you've provided with us on the call itself. So.
Great. And thank you very much, everyone, for participating in this workshop and for staying for 3 hours. Yeah, and we really value your input. That is very helpful for our planning of this seismic experiment. So thank you very much.
Thanks to all of our speakers as well.
Yeah, thank you to our speakers, and we will keep you posted on the progress of the development of this program. Thank you.
Yeah, and follow up with other mechanisms for you to be in touch with us so that we can move forward together as a community. So thank you very much.
Thank you.
Thank you. Bye.
Bye, everyone. Thank you.
Bye. Thank you.
You.